Hello students, how are you? So today is the second class of thermodynamics. In the previous class, we are being introduced to some of the terminologies which are, I think, very important for your upcoming lectures. So if I just make a quick revision of that. So first we told that okay, the system is the place where we are doing the work, and surrounding except the system, whatever with the universe you have is called as a surrounding. So if you just add the both the system plus surrounding, that would give you the universe. So this was the first thing that we dealt with, and it was of quite great significance. Okay. Now in the next part, we said that okay, the system and surrounding are just separated by a very you can say it may be an invisible or a visible wall or a boundary. Okay, so in terminologies also it is called as wall or boundary, and they can be of various types. Like one we studied was of adiabatic. Okay, so adiabatic is one which does not allow the passage of heat, so it does not allow heat to go in or heat to go out. Okay, clear. So the work that was done inside that adiabatic wall is called as adiabatic work. So that are the things we got studied, and plus we got introduced to the first law of thermodynamics, whose statement was that energy can be converted from from to another. It cannot be destroyed. Basically, it is the law that is defined by the mathematical expression delta U is equals to Q plus W, where delta U was the change in internal energy. So internal energy, you can think of it as the total energy that is constituted by a system. Okay. Now we said that if there is a change in internal energy, that it can be done in two ways. In two ways we can change it. First of all, if we provide heat, or if we extract heat. The first thing was heat. The second thing was work. So if you do work on the system or the system does some work, so in both cases your internal energy will change. Okay, so these are the two ways we can change the energy of a system. Okay, but this is a cover. This is quite a very good approximation. It works with most of the system, but there are systems which does not go in hand with this Q plus W thing. There are systems that will go against this. So we will not focus on that. So today we will just look upon these two, that is Q and W, that how we can change the internal energy by doing work or by applying heat. Clear? We will just try to quantify that thing, that how it changes through expressions. Okay, through mathematical expressions, I would say specifically. So first of all, we will deal with work. Okay, so work, I think, is very important to be in a chemical reaction. So whenever we do a reaction, most of the reaction that we do are either in the liquid phase or in the gaseous phase, and the gases that are produced can of course do mechanical work, or it can generate heat. So we should have a device to say calculate the work that has been done. Clear? So this work is clearly related with the internal energy. So first, let us see how does this work is quantified. How the work is quantified. Okay, so let us consider a piston. So what is a piston? You can just think of the air pump that you use in your in pumping bicycles and filling them with air. So that piston can be considered, which you just press it and put it down. Now suppose that piston is put upon a volume. Means the volume that has been contained inside the piston along with the container is Vi, and you are applying P external pressure through that pump. Okay, now suppose the volume has been changed from V initial to V final. So basically we have compressed that gas. Okay, we have just compressed that gas with the help of force, okay, or by applying pressure through the piston. So this is the diagram representation of that. So suppose this is your initial condition in which your piston is here. Okay, your volume that is contained, it is this, that is V initial, that is denoted with Vi. Now suppose you are applying pressure, the piston moved from here to here. Okay, and in that process your volume changes from Vi to Vf, that is V initial to V final. Now suppose I tell you that okay, this is the length of the movement and the area of cross section. So area of cross section is basically this area. Okay, this area, that is this circular area, or you can take the area of this piston also. Both are approximately same. So the change in the volume would be length into area, of course, right? Because length into area means length into area of cross section gives you the volume. So this is the volume. Suppose it is being moved. How we know that? Because we know the length that has been displaced, or the distance through which the piston has displaced, and we know the area of cross section. So this length multiplied by area of cross section will give you the change in volume, that is V final minus V initial. So this is the volume change. Okay. Now what is the uh, formula for pressure? It is force per unit area. Okay, it is force per unit area. Therefore, force will be equals to pressure into area. Right? Clear? Now, or work is equals to force into distance also. We know this also. Right? So therefore, work will be, so this will be your force P external into area, and work will be force into distance. So if you just multiply it by distance, so A into L will give you the volume. So this is the overall work. So again, let us just summarize this. So we know that pressure is equals to force by area. So force is equals to area into pressure, that is P external into the area. So this is the area of cross section. So we are talking about this area of cross section. And we know that work is equals to force into distance. W is equals to F dot D cos theta. That same formula is used here. Now since the force of means the direction of force and the direction of movement are both same, therefore the angle is what? The angle is 0 degree between both of these. So cos 0 degree is equals to 1. So that is you can say melt down to this F into D, means simple product of FD, because cos theta is already 1. Okay, so this is the thing. So P external into A dot length. Okay, so area into length. So we have just multiplied by the distance by which we have moved. Now A into L, we know it very well. We have just formulated it. It is change in volume, that is final minus initial. So we put this thing here, okay, with a negative sign. Why are we putting it with a negative sign? Because the volume has decreased, okay, or you can see that volume has decreased. So V final minus V initial has been changed. So V final minus V initial will give you which value, positive or negative? It will give you negative value. Because why it will give you negative value? Because V final is smaller. Okay, so that would give you a negative value. If you don't put a negative sign against it, then it will give you a negative work. But since we are doing work on the system, so as to maintain the IUPAC convention, so whenever we do work on the system, then the work done will be always what? It will be always positive. So this should be always in your mind. So it is just opposite to the concept that is being taught in physics. Okay, so in physics we take the opposite. Here we say that if the work that has been done, if it is done on the system, then the work should be positive. And if it is done by the system, means if suppose the gas would have expanded by its own, then it is called as work done by the system. Then in that case, the work done should come out to be negative. So to maintain that IUPAC convention, what do? We take a negative sign against it, so that the work is done by the system on the system should remain positive. So that would give you minus P external delta V. So this is P external. This should always be in your mind. It is not the pressure that is inside this pump, but it is the pressure that you are applying. So this is the difference between these two, right? So it is not the pressure that is inside the pump, but it is the pressure that you are applying. Therefore, this is the formula for work done, which is minus P external delta V. So this is a very important formula. We will use it to and fro. Now, since here we have moved a very small volume to move to a very, sorry, not a small volume, I would say, we have moved it in a one-way shot. Okay, so we have done it from here to here in one way, or you can say in one time. So we are using delta V. So when V final minus V initial. So this thing will change. Okay, for different type of process, it will change. So I'm just giving you a point here, so that when I change it, when I use a different formula, then you should remember that what I have told. Okay. Now, the negative sign of the expression is again the same thing written, is given to maintain the sign convention. Because here V final minus V initial will be negative, and that will give you the negative work. But since the work is done on the system, it is a compression work, therefore it should come out to be positive. Okay. So if the pressure is not constant and at each and every stage it is changing, then we use this formula. So this is the change that what I was talking about. Suppose we are not moving from V initial to V final at one shot. We are not just applying pressure in one shot and moving. What are we doing? We are doing it stepwise. Okay, so we are doing it stepwise. Suppose I have done it in this 1 2 3 4 5 6 steps. Okay, So for that, what we will do, we will suppose from here to here, this is the first step. Then you will calculate the pressure that has been used in this process and the volume that has been changed. Again, from here to here, the work done will be calculated. Here to here, the work done will be calculated. So for each step, you will calculate the work done. Here, the distance between the two volumes or the difference between the two volumes is large. So we are taking this formula. So when this distance becomes smaller and smaller, we will opt a different formula. Okay, so that would include integration also. Now we will not talk about this. So first of all, we are saying that we are moving from this volume to this volume, but in multiple steps. So what we can do is simply calculate the work in each step and just sum it all. So this sign shows the summation sign. So we will sum it all, and then it will give you the total work done. Clear? Now suppose what we are doing is we are moving from this volume to this volume in multiple steps, and in those multiple steps the change in volume is very small. Okay, the change in volume is very small. We are moving in such a way that the process become reversible. Okay, that the process become reversible. So what we do in a reversible process is we move through a very small infinitesimally small volume. Okay, and in that case the work done is reversible. So what is a reversible work done? If you just turn to the basic definition, then it says that it is that process in which from any point we can move back to the previous or the starting point. Okay, so that is called as reversible process. And in that reversible process, this thing is very much required, that if you are doing a work, you will do the work in such a way that the volume change is infinitesimally small. So we take that volume as dV. So delta V is something large. Okay, so delta represents something large difference. Okay, but dV represents a very small difference. Clear? So this is the difference between dV and delta V. Now what we will do, we will just integrate those small steps. So integration is basically what? It is kind of summing it all, but when it is used when we have a very small parts. Okay, so dV is a small part, so we will just integrate through the whole process. Okay, from V initial to V final, and the pressure that is applied is also remained constant at each step. So the pressure that is applied is constant at each step, and we are moving small volumes. Okay, we are moving small volumes. Therefore work will be given by negative integration of P external dV. Now this P external may be constant or may not be constant, but here when you will deal with various questions, then you will find that this P external is constant. Okay, now you will simply integrate it with dV, and that will give you the formula. Okay, so we will see the new formula. We will see it how it is derived. Now suppose here P external at each step is equals to P internal plus dP. So what is the meaning of this? So I have said that we are doing it in multiple steps. We are applying very small pressure and very amount of small pressure, and we are moving through a very small volume. Okay, so that is the case. Now your P external is almost equal to the P internal plus dP. So just let us first try to understand this. Okay, so why I am saying that? So I am applying dP pressure now. So why I am saying that P external is equal to P internal plus dP? So dP is the pressure that we add. So think it in this way. So here I have said that if you just come back here, so we are applying P external. So a pressure that is of course equal greater than the pressure that is inside it. Okay, clear? Now suppose a case arrives that we are not applying any pressure, means the outside pressure, that a P external and your P internal both are same. Now what you do, you just apply dP amount of work. Okay, dP means very small amount of work on this side. Now your final pressure will become P external plus dP. Okay, final pressure will become P external plus dP. Now this dP is very small. Okay, this is very small. Now if you just add this dP on this side, on the left side, okay, I am not doing it, means I am saying it just that if you if that dP, that plus dP is very small, so if you add that dP on the left hand side, so what you can say that P external is equals to P internal plus dP, right? Because I have said earlier that both of the pressure are equal, P internal and P external are equal, and now you are applying a very small pressure dP. So your final P external can be what? Written as in the terms of P internal plus dP. Is this clear? You got it? So what I am saying, again I am repeating it. So I am saying that initially suppose your internal and external pressure both are equal. Okay. Now what you have done, you have applied a very small pressure, that is dp. Clear? Now if I write your p external in terms of p internal, now your new p external, so in suppose initially p external it was p external 1, now suppose your new p external is will be equals to the internal pressure, okay, plus the dp amount of pressure that you have applied. Now if it was a case of expansion, then it would have been opposite, p internal minus dp, because we have released some pressure from the outside. So your new p external will be p internal minus dp. So in the general case, we can write p external is equals to p internal plus minus dp. Clear? So such a process in which we are doing such small steps is called as reversible process. Now a process is said to be, so just the basic definition is written here. The process is said to be reversible. So if a change is brought in such a way that from any point of movement it can be reversed by infinitesimal small change. Okay. Now a reversible process is very slow because it occurs in a number of equilibrium states. So what is the meaning of this? So what if you see here, then in each step we are attaining equilibrium. So we are going from one step to another, then from this step to this step. So there is a series of equilibrium steps, and the surrounding is almost in equilibrium with each other. The system and surrounding is almost equilibrium with each other, because we are creating a disturbance, but that disturbance is that much small that it is not disturbing your equilibrium, right? Okay, so coming back to the formula is very important. Now if that thing was done in the opposite way, then it is called as irreversible process. So that is the obvious definition of that. Now if you just put that formula, p internal plus minus dp, then this thing you will get. Okay, this is the thing you will get. Next, dp into dv. So if you multiply it with each of this, so this p internal into dv and dp into dv. Now p internal into dv will remain, whereas the dp and dv both are very small. So just think it of in this way. Suppose 10 to the power minus 36 into 10 to the power minus 46. So both are very small. If you just multiply them, then it is not always said that they will result in a greater number. They can even result in a more smaller number, and that is the case that has been seen here. So dp and dv both are small, so that will give you even a smaller value. Clear? And that can be neglected. So what you will do, you will just neglect that, okay, because that thing is added or subtracted. So if this dp dv is added or subtracted, it will give you the same value. So the final formula becomes p internal into dv. Okay, p internal into dv, right? Now you will know that p internal is the pressure inside the say container or the piston, and its formula is what? From the gas law we know that p is equals to nRT by v. To put those things here, then we get nRT dv by v. Clear? Is this thing clear? Okay, so we are doing this for the constant temperature. So the pressure is kept constant, that is why it is taken outside. Okay, it is taken outside the integration, and we are just integrating dv by v. So this is for constant temperature. Now when you integrate this dv by v, it will give you ln v, because 1 by v integration is what? Ln v. Now v final minus v initial, ln v final minus ln v initial, so that would give you ln v final by v initial. So this is the final formula. Now ln can be written in the form of 2.303 nRT log v final minus v by v initial with a negative sign. Is it clear? So this is the overall derivation of that. Okay, so this is a very important formula, and this is the work done in case of reversible, and that was the minus p external dv minus p external delta v was the work done in case of irreversible. So these are the two very important formulas. Now suppose you put this formula back, or you just equate it back to the equation that we have for the first law of thermodynamics, which is delta u is equals to q plus w. So you put the irreversible formula work done for irreversible work done. So if you put that formula here, so it will be delta u is equals to q minus p external delta v. Clear? Now suppose if the process is carried out in constant volume. Now we are looking upon different scenarios. So suppose the first scenario is that we are doing the work in such a way that there is no volume change. So delta V is equals to 0. So that will give you the final formula is delta U is equals to QV. So what does this QV mean? It means that the heat exchange is occurring at constant volume. So Q in subscript we are writing it as V. So it is not multiplied with Q. It is written it as a subscript where QV denotes the heat is supplied at constant volume. Clear? So two cases can arise. First is your P external can be 0. So if your P external is 0, which means that we are not applying any pressure. Okay. And in that case, if the gas, so if the P external is 0, then of course your gas will expand. So think it of in this way. Suppose you are opening the bottle of a Coke. Okay. Now your internal pressure is greater than the outside pressure. So as soon as you open the Coke's say Coke's opener, so if you open the Coke's lid, then the gas will come out quickly. Okay. So that is a kind of free expansion only. Here also the P external is what? It is 0, means we are not applying any pressure. Then the frictionless piston will move and it will result in expansion. Okay, it will result in free expansion. So this is called as free expansion when the external pressure is 0. Clear? Now if your P external is 0, then the work done is also 0. Okay, so W will be also 0. Clear? Now so that is the same thing written here. So no work is done during free expansion of an ideal gas, whether the process is irreversible or reversible. So this is true for both irreversible and reversible, that the work done in free expansion is 0. Now this is the second scenario. First scenario is we are taking del V as 0, therefore work done is 0, and hence this we are getting as the final formula delta U is equals to QV, where QV is the heat exchange at constant volume. And the second scenario is that the external pressure is 0, and that is the reason we are getting no work done. Okay, and that is true for both reversible and irreversible process. Okay. Now for isothermal process expansion of gas into vacuum. So what we have done, so we have taken isothermal expansion, but we have kept the P external as 0. Means we are doing the process in vacuum region. So that would result in work done also 0. So also Joule determined experimentally that Q is also equal to 0. Means if you do the isothermal expansion of gas in vacuum, then both W and Q both are 0. So this is experimentally determined thing. Okay, it is experimentally determined thing that both work done and Q are 0 at isothermal expansion of a gas in a vacuum. Okay, so free expansion of a gas in isothermal condition will give you W and Q both 0, and that will result in no change in the internal energy, because internal energy is simply Q plus W. So if your expansion is taking place as a free expansion or in the vacuum region, then both and your conditions are isothermal, then your both work done and heat exchange is 0, and therefore your change in internal energy is also 0. Clear? Okay, next, for isothermal process delta U is 0. This is the next case. So you will get will know later on where is this coming from, that for isothermal process your delta U is 0. Just you have to consider it for just now that okay, in case of isothermal process the delta U is 0. So whether it is reversible or irreversible, in both cases your delta U will be 0. Okay, now a very important thing, this is a path function. Okay, so we have two functions, this is a state function. Delta U is a state function, so it only depends upon the initial and final state. Therefore for this reason, so whether we do the work by reversible process or by irreversible process, now since these are both paths, okay, if you remember, then these are both are two types of path that can be acquired for doing the thing. So you can do a work using the reversible path, or you can do a work by using a irreversible path. So if your delta U is 0 in one scenario, then it will be 0 in both scenarios, because delta U is independent of path. So therefore for both reversible and irreversible process, if it is isothermal, delta U is 0. Now why it is 0 in isothermal process, that we will discuss later. Okay, so first let us consider that for isothermal process, delta U is 0. Therefore, Q is equals to minus W. Okay, because delta U is equals to Q plus W. Therefore, Q is equals to minus W. And W formula is what? Work done is given by minus P external V final minus V initial. So minus minus gets cancelled out, and you will get this for this finally. Okay. Now, if you consider it for reversible process, then this is the final formula. So in both cases, your delta U is taken as 0. Clear? So this is for irreversible and this is for reversible. Now suppose we take a different process, that is adiabatic. So that means that Q is equals to 0, because we have said that adiabatic means the heat exchange that is been taking place is 0. Okay, so therefore delta U is equals to QWAD. So WAD means work done in adiabatic conditions. Okay, clear? Okay, now we will talk about it. Okay, so let us talk about this new state function. So we already knew that at constant volume, delta U is given by QV. What is QV here? It is the heat exchange at constant volume. Okay, this is clear. Now, most of the reaction are carried out at constant volume, but in flux or test tube under constant atmospheric pressure. Okay, so the one thing we know that most of our reactions that we see are not carried out at constant volume, but they are carried out at constant pressure. So for that, we need to define something new. Okay, we need to define something new, some new variable that would be more appropriate. So if you just think of it in a way, suppose you are doing any reaction in a lab. Okay, so in a lab, what you will do, you will not adjust the pressure. Okay, most of the reactions are carried out at normal pressure that we see day to day. Okay, there are reactions that require very high pressure or low pressure. That is a different thing. But most of the reactions are carried out at at constant pressure or at atmospheric pressure. But the volume change is obvious. Okay, so for constant pressure, we have to define a new variable. Now this is the formula that we know, QP minus P delta V, where QP is the heat absorbed at constant pressure and minus P delta V represent expansion work done by the system. Now let us represent the initial and final state by V1 by 1 and 2. So you can write here that for first condition U1 is equals to, okay, you can write, so if these are the two cases, then you can write it as U1 is equals to what? U1 is equals to minus P V1 and U2 is equals to minus P V2. Okay, therefore QP will be equals to what? QP will be equals to U2 plus PV2 minus U1 plus PV1. If you just rearrange this, then you can write this thing. Okay, now this QP that is being mentioned here, so that QP is called as delta H. Okay, that is called as delta H. So now you have two definitions of heats. Okay, so heat exchange can be at constant volume, and that is called as internal energy. And if your heat exchange it as constant pressure, then that is called as H or enthalpy. Okay, so these are the two definitions. And again, one more thing, enthalpy is also a state function. So if you can calculate the heat change at heat change at constant pressure, then you can use it. Okay, so I will just pronounce this or signify the importance of this formula later on. But just for now, just consider these two formulas very, very important, that delta U is equals to QV, that is heat change at constant volume, and delta H is equals to QP, which is heat change at constant pressure. Clear? So what we did here is we have taken two conditions. Okay, first state and second state, which is subscripted as 1 and 2. And for both conditions, we have written U. Clear? And we have just rearranged it and find the value of QP, which is equals to this. Now we are saying that this is a new function which we will term as H, which is nothing but your internal energy plus the work done. Okay, sorry, internal energy plus PV. Okay, similarly this is internal energy 1 plus PV. So these two are H2 and H1, and H2 minus H1 we are saying it as delta H. Clear? Okay, now although Q is the path dependent function and h is a state dependent function. So this is the very difference between both of this. So q is dependent upon path. So again I am repeating it. What is the meaning of this? So if you are arriving from one state to another state to through two different paths. Suppose you are one is in one process you are arriving through what? You are arriving through reversible process. Okay, reversible path, and in the other path you are taking the irreversible path. Okay, now but you are reaching at the same destination or at the same state. So what is the meaning of this? That we are saying that same state means pressure, volume and temperature is same. The final pressure and volume and temperature are same, independent of the path we are taking. So that is same. So if we are doing that or we are taking that two paths, now if you calculate the work done or if you calculate the heat exchange, then these both terms can be different for both paths. Although we are reaching the same destination or although we are reaching the same state, then also your work done and heat change will be different for both irreversible and reversible path. But if you take the case of enthalpy or your say internal energy, so these functions are state functions. So the value for these functions will be same. Clear? So if you take either of the path, you will get the same internal energy. So this is the basic difference between state function and path function. Therefore, delta H is independent of path and QP is also independent of path. So here is the twist, that since you're at constant pressure, the heat is called as enthalpy. Therefore, when the heat change is occurring at constant pressure, we call it as state function. So in the general case, we call the heat as path function. But when you are doing the heat change at constant volume or at constant pressure, then in both scenarios, we will call that heat exchange, or the heat exchange is called as state function, because at constant volume, that heat exchange is the internal energy, which is state function, and at constant pressure the heat exchanges enthalpy, which is also a state function. Clear? Now for finite change, we can write this formula: delta H is equals to delta U plus P delta PV. So here if you see clearly, if the pressure and volume are both changing, then we have to do P2 minus P2 V2 minus P1 V1. If one is constant, then this delta will just carry, because you can think it of it as a differentiation. Okay, so if you take the difference, suppose if this is constant, this will come out, and we will the final formula will be delta H is equals to delta U plus P delta V. Or if your pressure is changing and volume is not changing, then volume will come out. Clear? Okay. So the same thing written here, that if your pressure is constant, then your formula becomes delta H is equals to delta U plus P delta V. Clear? Now again we are taking that different scenario, means if we are taking QV, suppose if you are taking QV, then we can write delta U is equals to QV. Okay, we know that at constant volume, right? So delta H is negative for exothermic process and positive for endothermic process. So this is very important. Okay, so if your work done, so if you are doing a process and in that process, suppose the heat is evolved. Okay, if the heat is evolved, then we call it as what? We call it as exothermic process, and delta H is negative in that case. And if the heat is gained by the system or it is absorbed by the system, then in that case we call it as endothermic process, and delta H is positive in that case. Clear? Okay. Now if you take constant pressure also, and further if you take the constant volume also, then your this term P delta V will become 0. Okay, and at constant volume we call delta U as QV, right? So the whole formula will become delta H is equals to delta U plus is equals to QV. So we are writing it from here. So what we are saying, so initially we have taken pressure as constant, now you are taking volume also constant. So that will give you delta H is equals to delta U, and at constant volume the heat change is called as QV. So we are writing here QV. Okay. Now the difference between delta H and delta U is not significant. What does it mean? So it is very, very important to understand that delta H and delta U is not very different from each other. These both terminologies are almost same. Okay, for solids and liquids. Because why it is so? Because solids and liquids do not undergo significant volume change. Okay, they do not undergo significant volume change under pressure. But this is not the case for what? This is not the case for any other state function. Okay, or you can, this is not the case for the gases, right? So the difference becomes significant when gases are considered. So for this, let us consider a reaction in which gases are involved. Suppose VA is the volume of the gaseous reactant initially, and VB is the volume of the gaseous reactant product side. Okay, so on the product side, the volume is VB, and the reactant side, the volume is VA. Now consider that the number of moles is Na, and the number of moles at product side is Nb. Right? Then using the gas law, we can write PVA is equals to NaRT and PVB is equals to NbRT. Therefore, we can write that PVB minus PVA. So we are calculating P delta V. Okay, P delta V. Okay, so we have calculated P delta V as this. Okay, so what we have done, we have just substituted this PVB, so which is equals to NbRT, and PVA, which is equals to NaRT. This will melt down to this form. Okay, now we can write P delta V is equals to delta NgRT. So P delta V is equals to delta NgRT. Hence, our formula becomes delta H is equals to delta U plus delta NgRT. So what are we doing is we are finding the value of P delta V for this equation. So we are calculating P delta V for this equation, which we got it as delta NgRT, and which we are substituting it back into the initial equation. So we got this thing. So this formula is very, very important. Here R and T are constant. So if you just take this out, then you can directly calculate delta H if you have delta U. And this is for gases. Why it is for gases? Because in case of gases, the volume change is significant, right? The volume change is significant. Now let us consider a problem here. So which says that if water vapor is assumed to be a perfect gas. Okay, so we are taking it as a perfect gas, means ideal gas. So PV is equals to nRT can be applied. Now the molar enthalpy change for vaporization, is taken for 1 mole of water at 1 bar, and at 100 degrees Celsius is 41 kilojoule. So what is the meaning of molar enthalpy change? It means that the enthalpy change is for 1 mole of what? 1 mole of water. Clear? Now calculate the internal energy when 1 mole of water is vaporized at 1 bar and 100 degrees Celsius. Okay, so we have to calculate the internal energy change. So we know this formula, delta H is equals to delta U plus NgRT, and this is the transition that we are going along. Now, if you see here this formula, it is written that it is for delta NgRT is for what? It is for gases. Okay, so here the change in number of moles of gas is 1, because on the reactant side we have 0 moles of gases, and here on the product side we have 1 mole of gases. Therefore, change in number of moles of gases will be 1. 1 minus 0, 1. Okay. Therefore, we can write it as delta U is equals to delta H minus delta NgRT. Now, delta Ng is 1. R value is given. We know it. It is 8.314 joule per Kelvin per mole in the SI terms. Temperature is also already mentioned. It is 100 degrees Celsius because boiling take place at 100 degrees Celsius. If it was not mentioned also, then we have to consider it as 100 degrees Celsius only. And delta H value is given as 41 kilojoule per mole. So you will convert this in joule per mole by multiplying into 10 to the power 3. Finally, you put this back here. So you will get your delta U as 37.904 kilojoule per mole. Clear? So what they have done is they have converted this value into kilojoule by dividing it by 10 to the power 3. So you can do either of them, but I would suggest you that you find your value in kilojoule per mole, because in joule per mole that would be more complicated to follow. Okay. So we have calculated this delta NgRT, converted it into kilojoule per mole, and finally we got this formula. So this is the value of delta U. Next is extensive property and intensive property. So this is also very, very important. So we have just differentiated state function and path function. So I think you should remember what is state function and path function. So state functions are those whose values depend upon initial and final value only. Path functions are those whose value also depend upon the path that we have taken to attain the final state. So if you take the examples of state function, then those are what? Then those are volume and your enthalpy change and say internal enthalpy change and internal energy change, or you can say that enthalpy and internal energy are both state function, whereas your heat exchange and your work done are path function. Clear? Okay. Now talking about extensive and intensive properties. So what are intensive and extensive properties? So extensive properties are those which depend upon the number of moles or the amount of substance which you have taken. Likewise, so suppose if you have a container, okay, if you have a container, now if you just measure the pressure inside it, then suppose it comes out to be 1 bar. Now what you do, uh, take a partition and put it in between, okay, such that there are now two compartments. Now if you just measure the pressure on both sides, then both pressures will be again 1 bar only, okay. So this signifies that that pressure is not dependent upon the number of moles, but it is independent on the number of moles. Clear? Got it? Okay. So I will just give you more and more examples of that. So extensive property is a property whose value depend upon the size and quantity of matter. Examples are mass, volume. Okay, so mass of course depend upon the number of moles. If you increase the number of moles, your mass will of course increase. If you increase the number of moles, your volume will also increase. Right? Internal energy, enthalpy, heat capacity, all are extensive property. Whereas those value does not depend upon the number of particles are called as intensive property. Examples like molar properties, all the properties which are defined for 1 mole, like molar enthalpy change, molar internal change, so that are defined for 1 mole. So it is independent of the number of moles. Clear? So examples are temperature, density, pressure, etc. So how can we know this? So there is a very simple experiment for that you can just conduct in your mind also. So what you do, so that same process that I have told, I will do it in the reverse way now. That would be more appropriate. So you take a container, put a partition in between, fill the both compartments. You will get two compartments. Fill both compartments with air. Okay. Now what you do here is that such that the pressure in both compartments are same, volume in both compartments are same, and temperature in both compartments are same. Okay. Now calculate. So V1 and V2 is the volume. Sorry, V1 and V2. Suppose V1 is the volume in both compartments, P1 is the pressure in both compartments, and T1 is the temperature in both compartments. Now what you do, you slightly lift that barrier. So once you lift that barrier, both the gases will converge and they will just come in contact with each other. Now you calculate the pressure, volume and temperature. You will see that initially the pressure was P1, then in the final case also the pressure remains P1, because see, initially here it was also P1, here is what also P1. So if they will combine, there will be no change of pressure. Suppose the density is also mentioned T1. Now the density will also not change, okay, but the volume will be different, because now it will be V1 plus V1, that will be 2V1. Temperature will not change. So if your room's temperature is suppose 45 degrees Celsius, and besides the room it is also 45 degrees Celsius. Now if you remove the wall between the two rooms, then the final temperature would also be 45 degrees Celsius. Clear? So in this way, if you just divide your compartments and just observe the properties, and after removing that barrier, or after lifting that barrier, you got the same value of the variables that you have taken, then those variables will be intensive and the remaining one will be extensive. Clear? Okay. Now talking about the molar properties that I was saying, that okay, some properties are molar, like it depends upon the number of moles. So what we are doing is we are defining it for 1 mole of a substance. Okay. Suppose this is your property that you are talking about. Okay. Now if you just divide it by the number of moles, so this property is what? This property is extensive property. Suppose it is enthalpy, okay, or it is internal energy. Now if you divide this value by n, that is number of moles, then your internal energy will be converted to molar internal energy, or enthalpy change will be converted to molar enthalpy change. Okay, so it is represented in this way. Suppose this is written as Vm, so it is the meaning, it means that it is the volume for 1 mole of a substance. Suppose it is written Cm, it means the heat capacity is for 1 mole of a substance. Got it? Okay. So the same experiment is being done here, which I have told you. So we have taken a container here which is having volume V and temperature T. Now we put a partition the temperature remains same in both the partitions, but the volume become half. So it is clear, and it is very clear that your volume is an extensive property because we have reduced the number of moles. Therefore, the volume has also decreased. Now, we have used a term here, heat capacity. So let us get clear about this terminology, which is heat capacity. So what is heat capacity? So if I just defined it in a basic way, then it means that if you want to raise the temperature of an amount of substance by 1 unit, okay, it can be 1 degree Celsius or 1 Kelvin, both are same. So if you want to raise the temperature of a system by 1 unit, that the amount of heat that you have to supply is called it as heat capacity. Right now, here the amount of substance is not specified, that whether this amount of substance is 1 kilogram or 1 mole or 1 gram, but we are saying that it is in general. Okay, so we are taking a certain amount of substance, we are raising the temperature by 1 unit, and the amount of heat that is being consumed in that process is called as heat capacity. So its formula would be what? Its formula would be Q by delta T. Sorry, yes, Q by delta T means heat supply for per unit temperature change. Clear? Okay. So it can be written in this way: Q is equals to C delta T, where C represent the heat capacity, delta T represent the change in temperature, and Q represent the heat. Now, what you do here is, suppose what you are doing, if you are supplying this heat at constant volume, then your heat capacity will also become Cv, and it will become, temperature will remain at T. Okay. So then your new form will be Qv is equals to Cv delta T. Similarly, if you are supplying your heat at constant pressure, then you will say it as Qp is equals to Cp delta T. Okay, clear? Now this heat capacity value is constant. It is almost constant, but it may change or it may vary with temperature, right? It may vary with temperature, but we don't have to consider that scenario. In that scenario, what you have to do, you have to write dt in place of delta T. Okay, you have to write dt means for a small temperature change, and C will be written as a function of temperature, and then you will integrate over the whole temperature range to get the value of C. Clear? Okay. Now coming back to our molar properties. So here we have the molar property of heat capacity. What we have done, we have taken the heat capacity and we have divided it by the number of moles with which the heat capacity is related. Then we will get the molar heat capacity, which is written as or symbolized as Cm. So it is the amount of temperature heat that is being supplied to raise the temperature by 1 degree Celsius of 1 mole of a substance, which is called as molar heat capacity. Similarly, we can write it for specific heat capacity also. In that case, rather than dividing by number of moles, we divide it by the mass of the substance that whose temperature is raised. Okay, so we get the heat supply that is required to raise the temperature for 1 gram of a substance. Suppose we are taking grams. Okay, we can take it as kg also. Next is, this formula is even simplified more. So the small c means the specific heat capacity, and suppose m is the mass. So if you multiply it with this, then you will get the q. Okay, it is easy to calculate. You just try it out, you will get this formula. So as I have told you earlier, if you are supplying heat at constant volume, then your formula becomes Qv is equals to Cv delta T. If you are doing it at constant pressure, then it becomes as Qp is equals to Cp delta T. Now we equate it with delta U, and you get a new formula of delta U, which is delta U is equals to Cv delta T. Now this whole relation is very, very important, okay? Because if your molar heat capacity is given at constant volume or your heat capacity is given at constant volume, then you can calculate the internal energy directly by knowing the temperature change. Okay. So coming back to this formula, so what we have done here, we have just substituted PV is equals to RT. Suppose your process is undergoing change under constant constant pressure and constant volume, but your temperature is changing. So you will substitute PV is equals to RT, and that will bring you to the formula delta H is equals to delta U plus R delta T, because R is a constant. Okay. So substituting the values here, so delta H is equals to Cp delta T, delta U is equals to Cv delta T, and PV is already substituted with R delta T. So if you just put this all, you will get it as Cp minus Cv is equals to R. So this is a very famous formula. So it is used to and fro in the questions and all to get your answer, because it is related directly to the gas constant. Okay, so it is molar heat capacity, sorry, it is heat capacity at constant pressure. This is heat capacity at constant volume. If you get the difference of both, it will be equals to the gas constant. Okay, so this was for today's lecture. With this, I end my lecture. Thank you.